Welcome back to The Explainer. I am absolutely thrilled to have you here today. Quick note right off the bat, this explainer was proudly made by Forge College. Okay, let's dive right in. If you've been following along in our From EVM to SVM track, you know we literally just wrapped up a fantastic session on the foundations of cost modeling. We got our hands dirty, we manually inspected transaction logs, and we figured out exactly how to find those sneaky compute hotspots. But let's be real for a second. Nobody wants to manually eyeball logs for every single code change, right? I mean, who has the time? Today, we're graduating. We are moving from manual inspection to architecting a beautifully automated, reproducible cost estimation script that integrates right into your development pipeline.
Here is our blueprint for today. First, the automation leap. Second, choosing measurement sources. Third, the four-phase pipeline. Fourth, scripting the CI bouncer. Fifth, setting pass-fail policies. And finally, conclusion and next steps. Let's get to work.
Section 1, the automation leap. Let me paint a picture for you. It's late on a Friday afternoon. Your team is pushing an update to a core smart contract. A developer makes a tiny, seemingly innocent tweak to a loop in the program. Code reviews look fine, tests pass, it merges, and boom, it goes to mainnet. Suddenly, your compute usage skyrockets. What we have here is what I affectionately call the 40% oops. A subtle, lazy PR just inflated your transaction costs by 40%. On a high-throughput application, that tiny oops is suddenly burning through your treasury like wildfire. So how do we stop these budget-busting bugs from ever reaching production in the first place? Well, the hero of our story is the automated CI pipeline. By scripting a measurement step directly into your continuous integration setup, every single code push triggers a targeted transaction run. If the compute usage grows beyond an agreed-upon tolerance, the build fails. Period. It's a hard gate. Cost regressions simply never see the light of day. Moving on to Section 2, choosing measurement sources.
To build this automated safety valve, we need data. We have to figure out where we're actually pulling our compute unit numbers from. In the Solana ecosystem, you have a few different battlegrounds to choose from. Let's look at the main two, simulation versus committed execution. Simulation uses the simulateTransaction RPC call. It's incredibly fast, it's safe because it doesn't spend any real tokens, and it's highly deterministic. That makes it absolutely perfect for running on every single pull request. On the flip side, committed execution means actually sending the transaction to a devnet and waiting for confirmation. It gives you high fidelity, actually meaning it captures all that real-world noise and on-chain state, but it is slower. My advice, use simulation as your rapid-fire PR check and use committed execution for your deeper nightly merge to main verifications.
Now, there is a third option that gives you maximum control, and that's the local validator. You can enable debug-level logging and really get under the hood here. However, spinning up a local validator can be a bit heavy for standard CI pipelines unless you have your environment beautifully containerized. So it's fantastic for deep local profiling, but maybe keep it out of your rapid PR pipeline to start. Section 3, the four-phase pipeline. Now that we know where our data comes from, let's architect the schematic for the pipeline itself. We're building a minimalist, robust machine with 4 sequential steps. First, we prepare. This means loading up our key pairs and funding accounts on devnet or local. Second, we execute. We send our representative transactions either as a simulation or a live send. Third, we observe. This is where we parse the RPC responses or the logs to extract those precious compute units. And fourth, we report. We aggregate the results, compute our estimated costs, and generate that all-important pass or fail signal.
Let's look at Section 4, scripting the CI bouncer.
Let's zoom in on that final reporting phase. We need to write the code logic that acts as the bouncer at the door of your main branch. Now, the real magic happens with this simple conversion mechanism. Raw compute units are great for developers, sure, but when you're talking to product managers or looking at a treasury budget, you need a tangible cost estimate. So we map raw compute units to an estimated token-denominated cost using this equation. Estimated cost equals the base fee plus the compute units consumed multiplied by the unit price. It perfectly isolates the compute cost impact. Even if absolute currency values fluctuate on mainnet, this gives you a normalized baseline metric to spot regressions. But wait, how do we get that compute units consumed variable in the first place? Well, your script needs to play detective. It hunts through the RPC response logs looking for exactly this phrase, consumed blank units. A simple JavaScript regex, matching the word consumed, grabbing the digits, and ignoring the rest of the noise, will pluck that golden nugget of data right out of the logs. Once our script extracts the data and runs the math, it needs to output something useful. We don't just want a wall of text flying by in a terminal, we want a structured JSON report. It absolutely must include the scenario name, like token transfer, the mode, so whether it's simulated or committed, the consumed compute units, the estimated cost, and, crucially, a Boolean passed field. Outputting this as JSON means your CI pipeline can automatically read it and literally annotate your developer's pull request with a neat little pass or fail badge.
Moving to Section 5, Setting Pass-Fail Policies.
A bouncer is completely useless if they don't know the rules of the club, right? We have to configure our baseline expectations. Let's look at what a normal blueprint looks like so we can spot that 40% oops. For example, a simple Lamport transfer might consume around 150 units, so we cap our pass condition at 300 units. An SPL token transfer is a bit heavier, maybe around 600 units, so we set the safety cap at 1,000. And a really heavy custom program instruction might run around 2,000 units, so our fail condition is anything over 3,000. By encoding these baselines directly into your repository, the CI script instantly knows if a new code commit has basically violated the laws of physics for your specific app. Now, here's a massive pro tip for you. Do not set your pass-fail threshold to the exact baseline number. Blockchain execution can have minor fluctuations depending on network state or account data. I highly recommend setting a percentage tolerance, like 10%. If the baseline is 1,000 units, let it pass up to 1,100. This perfectly catches the massive budget-busting bugs while preventing those noisy, annoying CI failures that just end up frustrating your developers.
Finally, Section 6, Conclusion and Next Steps.
We've journeyed all the way from recognizing the danger of unchecked compute usage to blueprinting an automated defense system, so I leave you with this final provocative question. Are your CI pipelines actually ready to catch the next 40% oops? If not, it's time to take action. Your immediate next step is to write a basic version of this script, run it locally against your own code, and collect those initial baselines. Lock those baselines into a JSON file and plug the whole shebang into your repo. Once you have these automated baselines, you are perfectly positioned for the next phase, which is deep optimization. Thank you so much for joining me on the Explainer today. As a quick reminder, this explainer was made by Forge College. I highly encourage you to head over to forge.college to master even more Web3 development topics, grab more blueprints, and really level up your skills. Until next time, keep building and keep optimizing.